Hi, and good morning, everyone. Welcome to the second day of the AADL ACVIP User Days. Today, we'll continue our program with presentations of the latest developments around AADL and ACVIP. First, we'll have our second keynote speaker. I am delighted Darren Cofer accepted to deliver a talk on Colin's efforts leveraging AADL for the assurance of cyber-physical systems. Then, Hazel Shackleton from Adventium Labs will present current effort to bridge SysML and AADL. This is an important step to ensure continuity across modeling efforts, and this is part of a larger digital engineering effort pushed forward by OSD. Finally, Michael Darling from GE will report on the Verdict toolset. Verdict combines multiple toolsets to ensure cyber system resiliency. Then, after a small lunch break, we will have two longer tutorial-like talks introducing AADL and ACVIP in more depth by the ACI and Adventium. But let us start with our keynote. It is my pleasure to introduce Darren Cofer. Darren Cofer is a fellow at Collins Aerospace and a veteran in developing and applying advanced analysis methods and tools for the verification and certification of high-integrity systems. Darren has been the PI on many projects for NASA, the NSA, IFR, or DARPA. Currently, Darren and his team are working on the DARPA case program, which is the topic of his talk today. So, thanks, Darren, and the floor is yours.
Thanks, Jerome. Yes, thank you for the invitation, and glad to be here to talk about the CASE program. And as Jerome mentioned, in addition to our team, there's other folks working on this program with DARPA, and Mike Darling from GE will talk about their work. It's kind of complementary and also involved with analysis of AADL architecture models for cybersecurity. Before jumping in too far, I want to mention the rest of our team here. So Collins is leading this team on the CASE program. CASE is Cyber Assured Systems Engineering. We're focusing on architectural transforms for cyber resilience, synthesis, formal analysis, tool integration. We have our colleagues from Data61 in Australia working with us on platform software, specifically the SEL4, formally verified microkernel, which we're integrating as a target for code generation. University of Kansas, Perry Alexander is working on verified attestation, remote attestation mechanisms for distributed computing. Adventium is working with us on real-time scheduling and AADL modeling and code generation. And finally, Kansas State University, John Hadcliffe and Robbie are working with us on automatic code generation and their HAMR framework for generating the infrastructure code from architecture models with proof equivalence. So the goals of the CASE program and what we're trying to implement with our BRIEFCASE tools are an integrated model-based system engineering tool suite based on AADL and with new capabilities related to transforming system designs to satisfy cyber resiliency requirements, how to build systems that by their design are robust against various cyber attacks. We're generating high assurance components from formal specifications. So some of these transforms require us to add new components to the system, and we're synthesizing those from their specs, verifying the overall system properties using our Agree compositional reasoning tool with model checking underneath. And then finally generating all of the software integration code from the AADL model directly from the verified models and targeting various operating systems, including SEL. And probably not a surprise to this audience, but reasons that we're choosing AADL as our modeling language is it provides us sufficiently rigorous semantics to support analysis. It's at the right level of abstraction for real-time distributed embedded systems that really are the core of our domain in the aerospace avionics world. And the OSATE tool, which supports addition of all the new capabilities that we need. So my talk is going to focus on kind of the three technology pillars that we're working with in the CASE program. So first of all, providing developer assistance to implement cyber resiliency as they're doing their design models. And so this involves tools that automate, provide various automated architectural transformations of the architectural models to mitigate threats that have been identified. There's a more general model-based system engineering theme specifically focused on cyber resiliency. And so this is where we're focused on how do we build the system directly from the AADL model and provide assurance that the system, the code that we build faithfully implements the model that we verified, and making the security guarantees of the SEL4 kernel accessible to system developers at the AADL level. And then finally, integrating a large collection of formal verification and proof evidence that's produced by all these different tools. And that goes from the foundational proofs of SEL4 correctness, the proofs of the code generation process from AADL, the proofs of the formally synthesized components that we generate, the system properties that we verify using the agree tool, integrating all of this evidence to give us a nice top to bottom assurance case demonstrating how and why the system requirements have been satisfied. So we'll go through each of these three categories. So first of all, here's sort of a map of the tools that we're developing and under this umbrella of briefcase. The top half of the diagram is really the system modeling environment focused around OSATE, and we've added a number of different plugins. The HAMR plugin for doing code generation. There's a couple of different plugins for generating cyber requirements from an initial model of the system. The Cyber Transform plugin for dealing with those requirements, and then the Agree and Resolute plugins that we've brought into the program for doing assumed guarantee reasoning. And Resolute is a tool for annotating an AADL model to produce and check an assurance case related to elements in the architecture model. The bottom half of the diagram is really about high assurance code generation. So that includes the SPLAT tool for synthesizing new components that we generate from their Agree specifications, all the specific mechanisms that HAMR uses for generating code and producing CAMKeys input models. CAMKeys is the component building system for SEL4, and then all the compilers that we use. We're also using the KML language that Data61 is developing for some of the high assurance components that we generate. So all of that high assurance code generation is the bottom half of the picture. So we'll refer to this as we go along. So the first topic, the first technology pillar, if you will, is this cyber resiliency transforms. Colored the pieces of the diagram that are relevant, but let's sort of go through the steps of the workflow that we're producing. So the first step is we'll start with some really just functional model of the system that we're trying to build. And then in the case program, we have researchers at CRA and Vanderbilt and Dahl Labs who have each built plugins that we can access through the Eclipse interface that can take in this AADL model. And they use different techniques for generating candidate cyber resiliency requirements based on different analysis they do using attack trees and so forth. But they're exploring the model structure and any of the annotations we've added to the model related to what components are trusted or where boundaries are in the system, external data links and so forth, to generate places where the model might be, the system might be subject to attack. So once these requirements are generated, we have a little wizard interface that allows us to import and manage these requirements. We can select them, we can tag them, we can give them meaningful names and associate them with formal properties in the system. And then those are imported into the model as goals, GSN goals in an assurance case that we're going to build to satisfy these requirements. So the idea is that there's a top level goal that says the system is cyber resilient. We decompose that by the specific requirements. And then each of the requirements that we imported is a sub goal in this assurance case that we're building up with the resolute notations in the AADL model. And then the next steps that we do will be to show how we satisfy each of those sub goals of what we do to the model to address those requirements. So that brings us to the second step, which is applying the cyber transformation. So we're providing the developers with kind of a library of different ways that the model can be transformed to address different cybersecurity issues. And this is obviously extensible within the framework. And the idea is that you take one of these cyber resiliency requirements. The wizard brings up an interface that allows you to say, oh, I'm going to address this, for example, a requirement that only well-formed requests are sent into the system. So I will insert a filter component that checks each of the messages and will drop messages that are not well-formed so we can avoid different types of code injection attacks, for example. So we have filters, monitors, attestation, different kind of gating components, virtualization that allows us to take legacy code and put it in a virtual machine on top of SEL4, and several other related things. So the idea is that the tool is not the developer still has to figure out what needs to be done, but we're trying to automate all of the dirty work of adding things and rerouting connections and moving things around to make sure that those are done correctly and without inadvertently making mistakes. And furthermore, once we insert one of these transforms or apply one of these transforms, this resolute assurance case gets augmented to add this transform as the strategy for how the requirement or goal is being addressed. So let's look at how that looks. So here's an example where we've inserted a filter, like I mentioned, and this just shows what some of the notation is, that we have a filter and a property associated with it. And whenever we do that from this library of resolute transforms, you can see that we've asserted sub-goals related to the filter strategy that says that the filter exists. That is, it hasn't been deleted inadvertently by some other operation that we do. It's not bypassable. So one of the key things about a filter is that all the messages have to actually go through it, and there's not some way that you can avoid going through the filter, and that the component has been correctly implemented. In this case, it's going to be by synthesis from its formal spec. And then once you do that, you can check these an assurance case. So one of the things that Resolute does that we've talked about in other presentations is allows you to actually evaluate the evidence that is attached to this assurance case that we're building up. So we can do, if the goal is something related to the model structure itself, Resolute can look at the model and see, is there a bypass path in the model, or has this filter been moved? And it can also call external tools like Agree to check whether the properties are satisfied or not. And so the idea is that it doesn't just give you a static tree, but it'll tell you whether the subtrees are satisfied because of the leaf level evidence being satisfied or not. So that's the idea, that in addition to doing these transforms, we're building this evidence infrastructure in the background that allows us to produce an assurance case at the end that documents why we believe the requirements are satisfied. So these some of the transforms like filters and monitors and attestation involve adding new components to the model. The splat tool takes the model interface, or the component interface, the data type for the inputs and outputs, and the property specified in agree, and it synthesizes an implementation for the component either in KML or C, along with a proof of showing why the source code actually implements the specification. And then there's other components. The attestation manager, for example, are actually pre-built, pre-verified libraries that that we bring in, and they have their own static proofs associated with them. So here's an example of how some of these things fit together. This is a CYBER-RETROFIT pattern, and it is one way that we might deal with legacy code or systems. So for example, we have some existing open source code that we want to use that may not have been originally developed for cybersecurity, or it's written in a language that we don't support natively, so it needs to run in a VM. So what we can do is take some of this functionality, run it in a virtual machine, and we can, with isolation guaranteed by the SEL4 microkernel, running in hypervisor mode, and we can support multiple virtual machines in this way. And then we might choose to extract or harden specific components. So for example, in this case, this component is a waypoint manager, and we need to be able to trust that we're always generating waypoints for our vehicle, no matter what happens, whether this the code inside of the VM runs correctly or not, because it is, in this case, not trusted code. So the waypoint manager ensures that we always have a backup route available to us. So we can pull that out and harden it, run it as a native component on SEL4. And then we might want to put a filter on the input side, a trusted filter that makes sure that any of the requests for new flight plans going in are actually well formed and can't inadvertently cause the flight planning system to crash. And then we might also monitor the outputs to check whether this legacy flight planning code is running correctly or not. So that kind of gives you an idea of how some of these transforms and components and mechanisms might work together in this CYBER-RETROFIT case. And the idea is that we start with kind of a basic functional model, we apply all these different transforms, and we end up with a transformed AADL model that looks like this in this UAD example. So that's a quick overview of the cyber resiliency transforms. The next topic I want to talk about is model-based system engineering for cybersecurity. These are the relevant parts of the tool. And a lot of our objective here is in common with all model-based system engineering work, and that is to build systems in a way that where the model actually is the system. It's not just a picture, it's not just for communication or a way to capture requirements, or maybe a means to perform analyses. Definitely it's all of those things, but we want our users, our developers, to think of the model as the system. This is actually how we're going to build the system, and do so in a way that ensures compliance of the final code on the airplane with the design captured in the model. This is very consistent with our rationale for choosing AADL. It provides the precision and semantics that we need for actually building real-time distributed embedded software systems. But one of the other important things that we want to do here is we've worked with the Data 61 developers of SEL4 for many years, going back to the HACMS program, the DARPA HACMS program. And there's a bit of a gap in making, it's not immediately straightforward to take a system and build it to run on SEL4. There's like any operating system, there's a lot of steps to be taken. And one of our objectives in this model-based system engineering for cybersecurity thrust is actually to bridge this gap between developers working at the model level in AADL, in our case, and their target SEL4 system. So we want to make the SEL4 goodness more accessible, easier for developers to use, essentially automating all the downstream build steps once you decide that that's what you're going to target. So we want to be able to promote successful transition of this technology into safety critical, mission critical, secure critical systems that we're building. And one of the means for doing that is the HAMR high assurance modeling for rapid engineering work that our KSU colleagues are doing. So this is the code generation work from the AADL models. So a little bit about HAMR and SEL4. So HAMR is a very nicely architected multi-stage translation system to address the case goals of being able to build components and target different, ultimately different execution platforms, operating systems, and processors, and to be able to guarantee that all the information flows that we define in our model are preserved when we go from the model to the deployed code. And we're using the same computation model across different platforms, and so far able to target not just SEL4, but also Linux and Linux VM running on SEL4, and some other prototyping applications. You can build your code to run on your workstation or on an emulator or on the actual embedded platform itself, an emulator like QEMU, for example. And then for those not familiar with SEL4, this is an L4 style microkernel. It guarantees that the separation of components and communication, all backed by computer checked proofs. So this is, I would maintain, the best you can do today in terms of being able to have a microkernel that has, where you have a formal proof that it is functionally correct and that its security properties of confidentiality and integrity, availability are true and proven all the way down to the binary. And it has really great performance as well. So the SEL14 motto is that security is no excuse for poor performance. So they've taken that into account as they are building and doing their proofs for the system. I mentioned that HAMR supports multiple languages and platform combinations. So this is just kind of a quick view of this at the very easy prototyping level. You can generate, have prototype code in the slang language and target a JVM to just run and kind of get the functional aspects of the system correct. You can build for C and run on Linux. You can run SEL4 in the QEMU emulator, and then you can also go direct onto your actual embedded platform. And so the idea is to be able to have the exact same AADL model and easily target all these different types of platforms that you need as you're moving from prototype system to actual deployed code. One of the keys to HAMR is the abstraction layers that are built up that allows it to tailor to the different platforms. So you can see on the left the different APIs for the port communication in and out of an AADL thread application code, and then on the bottom the thread APIs that control when threads are dispatched, when inputs are accessed, and when outputs are written, and all that. And then here's accompanying this mechanism is basically the idea is that you would have APIs that you write to for the inputs and the outputs, and for executing the business logic of a component that then HAMR interacts with. And so there's standardized entry points for the component. There's auto-generated code for the APIs for an event input point, and for an event port, and here's what it looks like for a data port. And we use the same C APIs are used for SEL4 native components or running on the VM, and there's similar APIs for Slang and CakeML that basically provide you the same sort of structure. One last tool that I'll mention in this category is RESOLINT, and as the name suggests, it's based on Resolute. This is a linter tool for AADL models, and so this came about because their AADL is a large language, and there's particular ways that we want users to construct their system in order for it to be compatible with the HAMR code generation, and also some analysis and other good practices, rules, and Resolute already provides us the ability to walk over the AADL model and gather up all the threads or all the input ports on threads that are running on a particular processor. You can make those kinds of queries in Resolute. It allows us to define rules that describe these, that capture these modeling guidelines. And these can be packaged up as a rule set, for example, for, what does it mean to be well-formed, to be compatible with HAMR. And you can check your model, and it gives you a nice output that tells you exactly where any problems or deficiencies are found. So this is a super useful and easily extendable tool. The last category of technologies that we'll talk about is the proof integration, and these are all the different parts of our system that are doing formal verification of some kind. And so the idea is that we're building up this stack of evidence from the binary at the bottom all the way up to the system properties at the top. And so the things on the bottom are really all of the data 61 proofs related to the SEL4 proof itself, the initializer, which gets you up and running to a system that can guarantee satisfying the configured properties, the CAM keys translation proof that guarantees that what you put into the CAM keys build system actually gives you the right SEL4 system configuration. The KSU folks are putting together a HAMR correspondence proof, which this is the proof that the AADL model has actually, the translated code implements that correctly in the CAM keys model. Then we have the high assurance components that implement properties of specific components in the system. We're not doing too much at this time with verification of any legacy components other than showing that their interfaces are correct. And we have the system properties and the architecture properties that are checked by the agree model checking tool. And then, as I mentioned, all of these things at the AADL model level are generating this Resolute assurance case skeleton as we build the system. And then one of the things that we're doing in this last phase of the case program is complete this assurance case to tie in all of the lower level proofs from the HAMR code generation, CAM keys translation, and SEL4 itself. So that's the idea. At the end, we'll have this assurance case that stitches together from top to bottom all of these different proof elements that we're producing. And oh yeah, if you remember that Blues Brothers album, this is sort of our motto for the program, the briefcase full of proofs. Yeah, I mentioned the bridging the gap at the model level. This is true at the proof level as well, that we have the SEL4 integrity policy and the proofs that this is enforced on a running system. There's a proof associated with the SEL4 system initializer that it constructs a system whose properties and objects conform to the capability specification that describes, who can talk to whom, who has access to what. CAM keys translates a system into a CAPDL spec, a capability specification, and then HAMR finally takes an AADL model, translates that to a CAM key system description. So these are all the pieces that get us from an AADL model down to a running SEL4 hosted system that implements all of the information flows and non-information flows that are shown in the AADL model. So a little more on this, this last step and what this looks like. So this is the HAMR correspondence proof concept. So the idea is that HAMR is generating a topological structure, and as it generates the code for that, it at the same time generates, uses Alloy to describe the relationships between ports and connections and threads. Then we end up with flow paths corresponding to the connections between ports and observation points in the code associated with the port inputs and port outputs. And then HAMR is also then generating traceability information between all these systems, these elements in the model and the corresponding elements in the executable code. And then after having generated this instrumented system, the proof that instruments this the system, we have two properties: one, flow preservation, so that every connection that's in the AADL model is in the generated code, and then going the other direction, that there's no new flows added. So for any flow path that's actually in the code should have a corresponding flow path in the model. So that's the idea there. And this mechanism, this proof concept is underway now. So we did we're partway through phase 3 of 3 in the CASE program. At the end of phase 2, we did a nice demo that showed how to use all these tools, targeting a small UAV. The very highest level AADL system description is on the top here. There's a ground station, and then the computing platform on the UAV that has inside of it a mission computer and a flight control computer. These all map to, so there's the ground station, the mission computer, which is this Odroid board, and then the flight control computer, which we just have an emulator for, is on board the aircraft is this Piccolo flight control computer. And the idea was that we built up an AADL model for this system. It has, as I mentioned in the CYBER-RETROFIT transform before, this UXAS mission planning software, which is developed by collaborators at AFRL. And the idea was to build a safe and secure implementation of that using our BRIEFCASE tools. And there's also another team in the CASE program led by Provotech, who's the evaluation team. And so it's their job to develop cyber attacks on the baseline platform. Then we harden it using our BRIEFCASE tools, and then they rerun those attacks. And so the idea is to show that our hardened system, the attacks are no longer effective in the hardened version of our system. So here's a simplified version of the AADL model. This pink process in the middle is the UXAS software that's been virtualized to run at a VM on SEL4. All the other components are running natively on SEL4. And so some of the attacks are, you might get malformed messages coming in over the radio link from the ground station that we want to filter out. The evaluation team actually put some Trojan code malware in the UXAS plan builder surface that would cause it to generate bad plans that violate the defined keep out zones for the system. And so we're trying to detect that. And then malware was also added to the ground station to generate malicious requests, tell the vehicle to fly somewhere that it shouldn't, or that the operator didn't intend. So all of the software on the mission computer is running on SEL4. The UXAS software is in a Linux VM virtualized on SEL4. So the specific attacks from the evaluation team were all mitigated. Malformed messages were blocked by a high assurance filter. We have a geofence monitor that detects plans that would violate the keep out zone and can cause the trusted waypoint manager to just return to base if we don't have a valid plan from the UXAS system. So it ensures that the vehicle stays safe. And then we use the remote attestation mechanism to measure the code running on the ground station, and we can determine whether it's been tampered with in any way. And if it has, then not trust commands that receive from it, and then can fall back to some known safe mission. So there's a lot in there. If you're interested in seeing how all of these pieces work together, Isaac Amundsen from our group put together a really nice tool demo that's on our project website at loonworks.com. So you can find that. Look for the case project, and you'll see a nice a tool demo that kind of walks through that workflow that I described. And then there's a part 2 video that then shows exactly this UAV implementation that we did at the end of phase 2 with all the different attacks. It shows kind of the before and after version of here's the attack being successful, and then here's the hardened code running, and you can see how we defeated the attack. So if you're interested, you can go and see both of those videos later. So just to wrap up, here's where we're at in phase 3. We're taking these tools and now applying them to a real avionics system on a mission computing system that Collins developed. So we have folks from our product area that we're working with and using these tools. So this is the Collins Common Avionics Architecture System, or CAS. And the baseline system has, it's a network computing system. It's got some synthetic vision system and some different nav databases and avionics and all kinds of other stuff, the ADSB that's receiving position information from other aircraft. And the idea in this scenario is to extend this system securely to add some wireless connectivity so that there can be wireless soldiers in the back of the aircraft. In this case, it's a CH-47 Chinook helicopter. Soldiers in the back can have tablets that can send and receive data securely with the avionics system, and the pilot might have a tablet that gives him some additional display capability. The method going forward here is to take one of these mission processing modules, the VPM here, and use it as a guard, reconfigure it as a guard using our briefcase tools. So here's the hardened system looks like this. The wireless, any traffic from this wireless router is now going to pass through this VPM. It has 2 independent network ports on it. And then we can kind of now separate the untrusted parts of the system from the trusted parts of the system, and include transforms on the VPN to filter messages, monitor traffic to look for spoofing, to do remote attestation on the tablet software to make sure that they haven't been compromised in any way, since they're just commercial tablets. So that the tablet would be running SEL4, hosting Android, or actually Linux. I think it's just a straight Linux with the application software running the other half of the attestation software. So that's what we're working on right now. Again, going through using all these different kinds of technologies, the cyber-resiliency transforms, the model-based system engineering mechanisms for cyber-resiliency and assured code generation, and integrating all of the different formal proof evidence that our tools are generating all along the way. There's the links again to the code. The code I should mention for these tools is all open source. That's where the Collins code lives. There's also links to all the different code from Kansas State, Data 61, everybody who's developing all the different pieces of tools, and then the case project page with the videos is on the loonworks.com site. And that is it. Thanks for listening.
Thanks a lot, Darren, and great talk. So we had a couple of questions. So I'm just trying to synthesize them because they were going in all type of directions, as you may imagine. So the first one is, and I'm going back to your previous slides, when you have been part of committees in charge of upgrading the 0178C, you may remember that part on model-based and formal verification. Mm-hmm. And one question is, what are your views on transitioning some of DAPA case contributions to actual projects? what does it mean to confront those contributions to airworthiness requirements and the type of tool qualification that you will have to achieve?
Right. So as you mentioned, there's two ways that fits into airworthiness. So one, this is obviously we're doing model-based development here. So there's a supplement to DO-178C that provides some additional guidance for use of model-based development tools. Maybe the more interesting area here is the DO-333 formal methods supplement, which provides some guidance on how and when you can take credit for formal verification evidence to satisfy some of the DO-178C objectives. As we've conceived this tool, most of the things that we would want to do would be you would be using formal methods tools for verification. So you would be qualifying tools as qualifying as a verification tool, which is TQL5 and the DO-178 lingo. And we kind of have that in mind as a method. This is probably more relevant for our commercial avionics business units, but to some extent that also applies to the military systems as well. Some of the components, the formally synthesized components, right now we're where we're generating code from a formal specification. I think we would also treat that as a verification property rather than qualifying the code generation process itself. We're emitting a proof that can be independently checked. And so it would still be a verification story showing you qualify the proof checker tool to show that the code generated actually implements the requirement specification. So yeah, this is a very long-term project, getting the airworthiness standards ready for receiving formal methods evidence from model-based development processes. So it'll be interesting to see if we can make all the different pieces come together.
Yeah. I'm really looking also towards into this, so thanks a lot. Another family of questions was related to the type of platforms you target. It seems that you were targeting a lot of ARM-based processors, Cortex-A, Cortex-M. Can you say a little bit more about those family of processors that you can support?
Yeah, that's right. And so if from a design standpoint, we want to run our code on SEL4, then we need to choose a platform for which there is SEL4 support. Those are primarily ARM platforms. There's also a verified x86 version that came out of the HACMS program. And again, the ARM processors supported depend on what capabilities that you need, whether you need to support virtualization or not. So then that determines which of the ARM processors you have a proof story for.
And do you think that this proof story can carry over multi-core systems?
So that is current research that the SEL4 team is working on now, the Trustworthy Systems team at the Data 61. They're very much working on extending the current proofs to multi-core settings. I think there's also a proof story for RISC, and this is something that we're looking at.
By RISC, you mean the RISC-V processors?
Yeah. The one thing that has been a bit of an issue is there isn't a proof story for any PowerPC, because that's
legacy, yeah.
That's essentially legacy, although it's still extremely widely used in avionics, but it hasn't been seen as worth developing trying to develop a proof story, because it's just not going to have the capabilities that we need going forward.
Yeah. If we go back to the modeling space, Darren, so you introduced the agree, resolute, and resolint, and one of the big, I would say, pushback against model-based is in some cases the capability to provide meaningful feedback from the tool to the designer. So I'm just curious about the type of feedback a tool like Resolint can provide in support of modeling activities?
Sure. So yeah, that is, and I totally agree with your concern. All of so RESOLINT is, and using Resolute, the feedback that you get is basically a visual tree of claims that tells you whether the specific rule has been violated or not, and it tells you where it's been violated. You get the context information. So that's good feedback for the developer. We've written the rules to be very specific so that you can kind of understand. You can put whatever English text you want in the feedback to explain what claim has been violated. The agree model checking, you tend to get sequences of steps. We're doing some really interesting work in other programs that are trying to take that kind of those counterexamples and display them in more of a signal flow tree form that maps back to the model itself, so that you can see, oh, this counterexample results in this signal being bad at this point in the model. So that's useful for debugging as well.
Yes, thanks a lot. So we just probably have a very last question, but probably a very broad one. So you know that at multiple points in your talk you mentioned virtual machines, and I'm just curious about what do you feel about this work and other trends that we see, like DevSecOps. Is it something that you feel connected with this idea of continuous pipeline from models to code in a DevOps continuous integration way of deploying software?
Yeah, so there's as a somebody from a avionics background, that's a relatively scary concept, right? We like the code on the airplane to be verified, deterministic, well understood, and then remain static. And there's definitely, as you mentioned, push to be more flexible, to be able to field new functionality more rapidly, more quickly. Certainly on the military side, that's the case. So it's true. You could look to mechanisms like the virtualization to essentially give you a sandbox where you can guarantee that no matter what happens in this virtual machine, it's maybe more flexible to run new experimental code, but you can guarantee that even if it crashes, the rest of the system, the hardened high assurance parts of the system, can continue to run and give you safety and security. And then you still have to manage the interfaces to that system, obviously, and that's where the filters and monitors and other mechanisms come into play. So I think it could provide a very strong part of that story to allow you to field new functionality on a continuous basis, but within a very strong hardened framework.
So a lot of interesting, cool stuff going on model-based. And thanks a lot, Darren, for your talk and answering all those questions.
Yeah, of course.
Thanks, everybody. And again, thanks to our speaker and audience.